is coming from number 7 in 15B. An alarm system has 20 batteries that are connected, so that when one battery fails, the next one takes over. So I've got battery A, and it's connected to battery B. And it's connected, I'm not a chemistry teacher, so I can't draw these properly. That's D, all the way up to the 20th battery. I should have given them numbers. Only one battery is working at a time. The batteries operate independently of each other, and each of them have a mean life of 7 hours. So what's the probability the alarm system is still working after 145 hours? So I might say T is my variable, where T is the total time of all 20 batteries. And T is going to equal battery 1 plus battery 2 plus battery 3 plus battery 4 plus battery 5 plus battery 6, all the way up to battery 20. And battery 1 works, and then when battery 1 fails and is dead, battery 2 kicks in. And then when battery 2 finishes, battery 3 kicks in. And when battery 3 finishes, battery 4 kicks in. These are all independent. Battery 2 doesn't start working until battery 1 is dead. Battery 2 won't affect battery 1. So I believe we have independent events, and I can use these rules, and I can use these rules for the expected value of each of them being added together. I'll work out the expected value of each of them added together, and I'll do the same thing for the variances. Okay, so now that I've understood the context of the question, then the expected value of T will be the expected value of battery 1 plus the expected value of battery 2 plus the expected value of battery 3 plus all the way through the expected value of battery 20. And since each of them have an expected value of 7, it's going to be 20 times 7, which is 140. Now, this is an additional process. I've got 20, I've got 7 plus 7 plus 7 plus 7 plus 7 plus all the way up to the 20th 7. That's where I get my 20 times 7. Not through the rule, but the addition of 7 20 times. And the variation of T will be 1 squared times the variation of battery 1 plus 1 squared plus the variation, times the variation of battery 2 plus 1 squared times the variation of battery 3 plus all the way up to 1 squared times the variation of battery 20. And the variations of each of the batteries are, what do we have? Standard deviation of 1/2. Therefore, the variation is 1/4. So I've got 1/4 plus 1/4 plus 1/4 plus 1/4, all the way up to the 20th 1/4, which gives me 20 times 1/4, which gives me 5. 4 goes into 25 times, is that correct? So the variation of T will be 5, so the standard deviation of T is √5. So now I know the total of the 20 batteries is normally distributed with a mean of 140 and a variation of 5, which is a standard deviation of √5. And I was able to use these rules to determine that. Now for the probability that the total is bigger than 145, I'm going to use the normal distribution because the total is normally distributed with a mean of 140 and a standard deviation of √5. And I'm looking for bigger than 145. So I'm going to do normal, CDF from 145 to infinity, mean is 140, standard deviation is √5 on my calculator. And I come up with interactive distribution, continuous, normal CDF, 145, upper is infinity, my standard deviation is √5, and my mean is 140. And I go OK. And correct number of arguments. What have I done? I put all of that in there by mistake. Comma, 140, close bracket, and that should be right now. And I get 0127. 0127 has been the probability of the combined batteries lasting more than 145 hours.